Imagine holding the master key to the universe, a single equation so elegant, so profound that it could unlock every mystery from the smallest quantum particle to the largest galaxy. Einstein spent the final decades of his life searching for it. Stephen Hawking called it the Holy Grail of physics. And today, the greatest minds in science are racing to discover what could be the most important breakthrough in human history. We call it the theory of everything, and it's closer than you might think. Right now, as you watch this video, reality is governed by forces so fundamentally different that they might as well exist in separate universes. Gravity keeps your feet on the ground, while electromagnetic forces light up your screen. Deep inside atomic nuclei, the strong force binds protons together, while the weak force triggers radioactive decay. These four fundamental forces have shaped everything that exists, yet they operate by completely different rules, follow different mathematics, and seem utterly incompatible with each other. But here's what will blow your mind. Hidden beneath this apparent chaos lies a deeper truth that could change everything we know about existence itself. Scientists are discovering that these seemingly unrelated forces might actually be different faces of a single, unified reality. And when we finally crack that code, we won't just understand how the universe works, we'll understand why it works. In this deep dive into the greatest quest in modern physics, we're going to explore the mind-bending theories that could unite all of reality into one elegant framework. We'll journey through 11 dimensions you can't see, investigate particles that exist in multiple places simultaneously, and discover why some of the smartest people who ever lived believe we're living inside a hologram. Now, prepare yourselves, we begin. But here's what makes this truly extraordinary. We're not just talking about abstract mathematics or theoretical curiosities. The discovery of a unified theory could revolutionize technology in ways that make the internet look primitive. We could harness energy from empty space itself, manipulate gravity like we manipulate electricity, and potentially unlock the secrets of time travel. The implications are so staggering that they border on science fiction, except the science is real and the breakthrough might happen in our lifetime. The story begins with a problem that has haunted physics for over a century. We have two incredibly successful theories that describe reality with breathtaking accuracy, yet they're completely incompatible with each other. It's like having two perfect maps of the same territory that show completely different landscapes. On one side, we have Einstein's general relativity, the theory that describes gravity and the large-scale structure of the universe. This theory tells us that massive objects warp the fabric of space and time, creating what we experience as gravitational attraction. It's been tested countless times and proven correct to extraordinary precision. When GPS satellites orbit Earth, they have to account for relativistic effects, or your navigation would be off by miles. When astronomers detect gravitational waves from colliding black holes, they're seeing Einstein's equations play out on a cosmic scale. On the other side, we have quantum mechanics, the theory that governs the microscopic world of atoms and subatomic particles. This theory reveals a reality so strange that it defies common sense. Particles can exist in multiple states simultaneously until observed. They can be entangled across vast distances, influencing each other instantaneously. They can tunnel through barriers that should be impossible to cross. Yet this bizarre theory has given us lasers, computers, MRI machines, and countless other technologies that define modern life. Both theories work perfectly within their own domains. The problem is that they give completely different descriptions of reality at its most fundamental level. General relativity describes a smooth, continuous spacetime where everything is deterministic and predictable. Quantum mechanics describes a grainy, probabilistic reality where uncertainty is built into the fabric of existence itself. This incompatibility becomes catastrophic when we try to understand situations where both theories should apply. What happens inside a black hole where gravity becomes so intense that quantum effects can't be ignored? What occurred in the first moments after the Big Bang, when the entire universe was compressed to quantum scales? How does gravity itself behave when we zoom in to the smallest possible distances where quantum fluctuations dominate everything? These questions have no answers because our two best theories give contradictory results. It's like trying to solve a puzzle where half the pieces come from one picture and half come from a completely different picture. Something fundamental is missing from our understanding of reality. The search for a unified theory began almost immediately after these incompatibilities were discovered. Einstein himself spent the last 30 years of his life trying to develop a unified field theory that would merge gravity with electromagnetism. He filled notebook after notebook with equations, exploring every mathematical pathway he could imagine. But he was working without knowledge of the strong and weak nuclear forces and without the sophisticated mathematical tools that would be developed decades later. Other brilliant physicists took up the challenge. They discovered that the electromagnetic force and weak nuclear force were actually different aspects of a single electroweak force. This breakthrough won multiple Nobel Prizes and proved that unification was possible. Then they showed how the electroweak force could be unified with the strong nuclear force in theories called grand unified theories. 3 of the 4 fundamental forces could be described as different aspects of a single underlying force. But gravity remained stubbornly separate. Every attempt to quantize gravity to make it compatible with quantum mechanics led to mathematical disasters. The equations produced infinite answers where finite answers were needed. The theory broke down at the smallest scales where it was supposed to provide answers. This is where our story takes a dramatic turn toward the truly extraordinary. In the 1960s and 70s, physicists began exploring a radical new idea. What if the fundamental building blocks of reality weren't point-like particles, but tiny, vibrating strings? These strings would be incredibly small, about 10 to the minus 35 meters in length. That's so small that if you scaled up a string to the size of an atom would be the size of the solar system. Different vibration patterns of these strings would correspond to different particles, just like a violin string can vibrate in different modes to produce different musical notes. These fundamental strings could vibrate in different patterns to produce electrons, quarks, photons, and all the other particles we observe in nature. This idea seemed almost absurdly speculative at first, but as physicists developed the mathematics, they made an astonishing discovery. String theory automatically included gravity. When they calculated how these vibrating strings would interact, one of the vibration patterns naturally corresponded to the graviton, the hypothetical particle that carries the gravitational force. For the first time, a single theoretical framework could describe all 4 fundamental forces. Gravity wasn't being forced into quantum mechanics against its will. It emerged naturally from the theory, like a musical note that appears automatically when you study the mathematics of vibrating strings. But string theory demanded an extraordinary price for this unification. The mathematics only worked consistently in specific numbers of dimensions, not the 3 dimensions of space plus 1 of time that we experience, but 10 or 11 total dimensions. The theory required 7 or 8 additional spatial dimensions beyond the 3 we can see. Where are these extra dimensions hiding? According to string theory, they're curled up at every point in space, compacted so small that we can't detect them directly. Imagine looking at a garden hose from far away. It appears to be a one-dimensional line. But zoom in closer and you discover it has additional circular dimensions wrapped around its length. String theory suggests that our familiar three-dimensional space might be like that garden hose, with additional dimensions curled up at scales too small for us to perceive. The geometry of these hidden dimensions would determine the properties of particles and forces we observe in our three-dimensional world. Different ways of curling up the extra dimensions would produce different physics. Some configurations might give us a universe with the particles and forces we know. Others might produce completely different realities with different types of matter and energy. This led to what physicists call the landscape problem. String theory doesn't predict a single unique universe. Instead, it allows for an enormous number of possible universes, perhaps 10 to the 500 different configurations. Each would have different physical laws, different particles, different values for fundamental constants like the strength of gravity or the mass of the electron. Critics argued that this made string theory unscientific. How can you test a theory that predicts almost every conceivable possibility? Supporters countered that this might actually explain why our universe has the properties it does. Perhaps we live in just one pocket of a vast multiverse, where every possible configuration of string theory plays out in different regions of space. But string theory's most radical implications were yet to be discovered. As physicists delved deeper into the mathematics, they uncovered connections so profound that they challenged our most basic assumptions about the nature of reality itself. The breakthrough came from an unexpected direction. While studying black holes through the lens of string theory, physicists discovered something that should have been impossible. They found that all the information about everything that falls into a black hole could be encoded on its two-dimensional surface. Every bit of data about the three-dimensional objects that crossed the event horizon could somehow be stored on the black hole's boundary. This discovery led to one of the most mind-bending ideas in modern physics. What if our entire three-dimensional reality is actually information encoded on a distant two-dimensional surface? What if everything you see, touch, and experience is essentially a hologram projected from this cosmic boundary? The holographic principle suggests that the volume of space we inhabit might be fundamentally illusory. All the information that describes every particle, every force, every interaction in our universe could be stored on a two-dimensional surface that we can never reach or directly observe. We would be like characters in a movie thinking we live in 3 dimensions while actually being patterns of light and shadow projected from a flat screen. This isn't just abstract philosophy. The mathematics works. Physicists have shown that certain quantum field theories in 3 dimensions are mathematically equivalent to gravitational theories in 4 dimensions. They can solve problems on one side of this correspondence and get answers that apply to the other side. It's as if they've discovered that 2 completely different languages are actually saying the same thing. But the holographic principle raises disturbing questions about the nature of free will and consciousness. If we're projections from a 2-dimensional boundary, are our thoughts and decisions real, or are we simply following patterns encoded in that distant surface? Some physicists argue that it doesn't matter. The projection is so perfect that our experiences remain valid regardless of their ultimate origin. Others worry that we might be discovering the limits of scientific knowledge itself. Meanwhile, string theory was evolving in directions that even its creators hadn't anticipated. Physicists discovered that what they thought were 5 different string theories were actually 5 different perspectives on the same underlying reality. Through mathematical transformations called dualities, they could show that seemingly different theories were describing the same physics from different viewpoints. This led to the development of M-theory, a framework that unified all string theories into a single theoretical structure. M-theory required 11 dimensions instead of 10, adding yet another spatial dimension to the already exotic landscape of extra dimensions. The M could stand for membrane, matrix, mystery, or mother of all theories, depending on which physicist you asked. M theory suggested that strings weren't the only fundamental objects. The theory also included higher dimensional objects called branes, short for membranes. These could be two-dimensional surfaces, three-dimensional volumes, or even higher dimensional structures existing in the 11-dimensional space. Our entire observable universe might be a three-dimensional brane floating in this higher dimensional space. All the particles and forces we know would be confined to our brain, like insects crawling on the surface of a sheet of paper. Only gravity would be able to propagate through the full 11-dimensional bulk, which might explain why gravity is so much weaker than the other fundamental forces. This brain world scenario opened up extraordinary possibilities. There might be other branes parallel to ours, hosting their own universes with their own versions of physics. Occasionally, these branes might collide, creating the conditions for a Big Bang. Our universe's birth might have been the result of such a collision, and future collisions could create new universes or destroy existing ones. The mathematics of M theory also revealed deep connections between seemingly unrelated areas of physics and mathematics. Equations that described the behavior of strongly interacting particles turned out to be equivalent to equations describing gravity in higher dimensions. This correspondence, known as the ADS-CFT correspondence, provided physicists with powerful new tools for solving previously intractable problems. But perhaps the most profound implication of M theory was its suggestion that space and time themselves might be emergent properties rather than fundamental features of reality. Just as temperature emerges from the collective motion of molecules, space-time might emerge from more basic underlying structures. The smooth, continuous space-time described by Einstein's relativity might be an approximation that works at large scales, but breaks down when we examine reality at its most fundamental level. This idea gained support from discoveries in quantum information theory. Physicists found that quantum entanglement, the mysterious connection between particles that Einstein called spooky action at a distance, might actually be responsible for weaving the fabric of space-time itself. When particles become entangled, they create geometric connections that could be the building blocks of space and time. Imagine space-time as a vast network of entangled quantum bits of information. The geometry of space would emerge from the pattern of entanglement between these bits. Distance would correspond to how strongly different regions are entangled. The curvature that creates gravity would arise from changes in the entanglement structure. This quantum origin of space-time could finally resolve the conflict between general relativity and quantum mechanics. Instead of trying to force gravity into the quantum world or quantum mechanics into the gravitational world, both would emerge from something deeper. Space, time, matter, and energy would all be different aspects of an underlying quantum information structure. The implications are staggering. If space-time is made of quantum information, then manipulating that information could allow us to manipulate the geometry of space itself. We might be able to create shortcuts through space by restructuring the entanglement patterns that give rise to distance. Wormholes, those hypothetical tunnels through space-time that appear in science fiction, might actually be possible by carefully arranging quantum entanglement. Even more remarkably, this view suggests that the universe might be fundamentally computational in nature. Every physical process would correspond to information processing operations. The evolution of the universe would be like a vast quantum computer calculating its own future states. We wouldn't just be living in a universe that can be described by mathematics. We would be living inside mathematics itself. But string theory and M theory aren't the only candidates for a theory of everything. Another approach, called loop quantum gravity, takes a completely different path toward unifying physics. Instead of starting with particles and forces, loop quantum gravity begins with space itself. This theory suggests that space isn't smooth and continuous as Einstein assumed, but is made up of tiny, discrete loops at the smallest possible scale. These loops are incredibly small, about 10 to the minus 35 meters across, the same scale where string theory operates. But instead of vibrating strings, loop quantum gravity proposes that space itself is woven from these fundamental loops like a cosmic fabric. In this picture, the familiar smooth space-time of general relativity emerges as an approximation, just like the smooth surface of water emerges from the chaotic motion of individual molecules. At the largest scales, space appears continuous, but zoom in far enough and you would see the discrete quantum structure that underlies all of reality. Loop quantum gravity makes specific predictions about the nature of black holes and the Big Bang that differ from string theory. It suggests that black holes don't destroy information, but rather transform it, creating white holes that spew information back into the universe. The Big Bang wouldn't be the beginning of time, but rather a big bounce, where a previous contracting universe rebounded into expansion. These competing theories represent different philosophical approaches to understanding reality. String theory embraces the idea of extra dimensions and multiple universes, suggesting that our familiar world is just one small corner of a vast, largely hidden cosmos. Loop quantum gravity stays closer to the observable universe, focusing on the quantum nature of space and time themselves without requiring additional dimensions. Yet both theories face enormous challenges in connecting their exotic mathematics to observable phenomena. The energies required to directly test string theory or loop quantum gravity are far beyond what any conceivable experiment could achieve. The scales involved are so small that they might forever remain beyond direct observation. This has led some physicists to explore alternative approaches that might be more amenable to experimental testing. One promising direction involves studying quantum gravity effects in systems that we can actually observe and manipulate in laboratories. Certain condensed matter systems, like exotic superconductors or quantum magnets, can exhibit behaviors that mirror the mathematics of quantum gravity. By studying these analog systems, physicists hope to gain insights into quantum gravity without needing to probe the Planck scale directly. Another approach involves looking for subtle signatures of quantum gravity in cosmological observations. The cosmic microwave background radiation, gravitational waves from the early universe, or the distribution of galaxies might carry imprints of the quantum nature of spacetime. These effects would be incredibly subtle, but advancing technology might eventually make them detectable. The search for quantum gravity has also revealed unexpected connections between physics and other fields of mathematics and computer science. The holographic principle has deep ties to information theory and quantum computation. The emergence of spacetime from entanglement connects to network theory and complex systems. The mathematical structures of string theory have led to breakthroughs in pure mathematics. These interdisciplinary connections suggest that the theory of everything might not just unify physics, but could also unify our understanding of information, computation, consciousness, and reality itself. We might be approaching a conceptual revolution that transforms not just science, but our entire world view. But perhaps the most revolutionary aspect of these unified theories isn't their mathematical elegance or their exotic predictions about extra dimensions. It's what they tell us about the fundamental nature of information itself. Deep within the equations of both string theory and loop quantum gravity lies a startling revelation that's reshaping how we think about everything from consciousness to the origin of the universe. Information, it turns out, might be more fundamental than matter and energy. This isn't just philosophical speculation, it's written into the mathematics of quantum mechanics itself. Every quantum system can be described in terms of the information it contains. Every physical process can be understood as information processing. Every measurement extracts information from the quantum world and transforms it into classical reality. The implications are mind-bending. If information is truly fundamental, then the universe isn't just described by mathematics. The universe is mathematics. Every particle, every force, every interaction is ultimately a pattern of information processing. We're not just living in a universe that follows mathematical laws. We're living inside a vast cosmic computation. This computational view of reality explains why certain problems in physics have been so difficult to solve. Trying to predict the behavior of strongly interacting quantum systems is like trying to simulate a computer on that same computer. The calculation becomes as complex as the system itself. There are no shortcuts because you're not just modeling reality, you're watching reality compute itself. But here's where it gets even stranger. If the universe is fundamentally computational, then it should be possible to perform calculations that are impossible for any conventional computer. Nature routinely solves quantum mechanical problems that would take classical computers longer than the age of the universe to complete. Every photosynthesis reaction, every chemical bond formation, every quantum measurement is solving computational problems at speeds that defy classical physics. Scientists are already beginning to harness this quantum computational power. Quantum computers use the strange properties of quantum mechanics to perform certain calculations exponentially faster than classical computers. They exploit superposition, allowing quantum bits to exist in multiple states simultaneously. They use entanglement to create correlations between quantum bits that have no classical analog. But quantum computers are just the beginning. If we can fully understand how the universe processes information at its most fundamental level, we might be able to build computational systems that rival the universe itself in their problem-solving capabilities. We could simulate entire universes, design new forms of matter, or solve optimization problems that are currently intractable. The connection between information and gravity opens up even more extraordinary possibilities. If spacetime emerges from quantum entanglement, then manipulating entanglement should allow us to manipulate the geometry of space itself. We could potentially create regions of space with different gravitational properties, or even build bridges through higher dimensional space that connect distant regions of our universe. These aren't just science fiction fantasies. The mathematics is real, even if the technology is still far beyond our current capabilities. Every major breakthrough in physics has eventually led to technologies that were unimaginable when the theories were first developed. Quantum mechanics gave us lasers, computers, and MRI machines. Relativity gave us GPS, nuclear power, and our understanding of stellar evolution. A complete theory of everything could revolutionize technology in ways that make the digital revolution look like a minor upgrade. We might learn to manipulate matter at the most fundamental level, creating materials with properties that seem magical by today's standards. We could harness energy sources that dwarf anything currently available, possibly extracting power from the quantum fluctuations of empty space itself. But the most profound impact might be on our understanding of consciousness itself. If information is fundamental, and if the universe is essentially a vast information processing system, then consciousness might not be something separate from physics. It might be what information processing feels like from the inside. This perspective suggests that consciousness isn't limited to biological brains. Any sufficiently complex information processing system could potentially exhibit conscious awareness. The universe itself, processing information at every level from quantum to cosmic, might possess some form of consciousness that we can barely imagine. Some physicists have proposed that consciousness plays a fundamental role in quantum mechanics. The act of measurement, which transforms quantum possibilities into definite realities, might require conscious observation. If this is true, then consciousness isn't just an accidental byproduct of cosmic evolution, it's woven into the fabric of reality at the most basic level. But these ideas push us toward philosophical territory that makes even the most speculative physics seem conservative. If consciousness is fundamental, what does that mean for free will? If the universe is computational, are we just following a predetermined algorithm? If reality is information, what distinguishes real experiences from simulated ones? These questions don't have clear answers, but they're becoming increasingly important as our scientific understanding approaches the deepest levels of reality. The theory of everything isn't just about unifying forces and particles. It's about understanding the relationship between mind and matter, between information and experience, between the physical and the conscious. Meanwhile, experimental physicists are pushing the boundaries of what we can observe and measure. New generations of particle accelerators probe higher energies and smaller scales. Gravitational wave detectors listen for ripples in spacetime that could carry signatures of quantum gravity. Space-based telescopes search for cosmic phenomena that might reveal the hidden dimensions or extra structure predicted by unified theories. The Large Hadron Collider has already discovered the Higgs boson, confirming the last piece of the standard model of particle physics. But physicists are eager to find something beyond the standard model, some sign that points toward the deeper unified theory. They're looking for evidence of supersymmetry, extra dimensions, or exotic particles that could validate string theory or other approaches to quantum gravity. Dark matter and dark energy present tantalizing clues about physics beyond our current understanding. These mysterious components make up 95% of the universe, yet we have no idea what they actually are. The theory of everything might finally explain these cosmic puzzles, revealing that dark matter consists of particles from hidden dimensions, or that dark energy arises from the quantum structure of spacetime itself. Cosmological observations are also pushing toward quantum gravity. The cosmic microwave background radiation preserves information about the universe when it was only 380,000 years old. Future missions might detect even earlier signals, perhaps even gravitational waves from cosmic inflation that occurred just moments after the Big Bang. These primordial signals could carry fingerprints of the quantum nature of spacetime. But perhaps the most exciting developments are happening at the intersection of theory and computation. Artificial intelligence is beginning to play a crucial role in theoretical physics, helping scientists navigate the vast landscape of possible theories and identify the most promising approaches. Machine learning algorithms can spot patterns in data that human physicists might miss, or explore mathematical structures too complex for traditional analysis. Some researchers are even using AI to generate new theoretical ideas. Neural networks trained on existing physics knowledge can propose novel mathematical structures or suggest unexpected connections between different areas of theory. While these AI-generated ideas still require human insight to evaluate and develop, they're expanding the space of possibilities that physicists can explore. The convergence of artificial intelligence and fundamental physics might accelerate the search for a theory of everything in ways we can't yet imagine. Just as the development of calculus was essential for Newton's mechanics, and tensor calculus was necessary for Einstein's relativity, new mathematical and computational tools might be required to finally crack the code of quantum gravity. But even with all these technological advances, the path to a theory of everything remains uncertain. The mathematical structures involved are so complex that even the most powerful computers struggle to explore all their implications. The energy scales involved are so extreme that direct experimental verification might be impossible with any foreseeable technology, yet the quest continues, driven by humanity's deepest impulse to understand our place in the cosmos. Every generation of physicists builds on the work of their predecessors, pushing the boundaries of knowledge a little further. The theories we're exploring today might seem as primitive to future scientists as medieval cosmology seems to us. But each step forward brings us closer to the ultimate goal. The stakes couldn't be higher. A complete understanding of reality's fundamental structure wouldn't just satisfy human curiosity, it would give us unprecedented power to shape the universe around us. We could potentially transcend the physical limitations that have constrained life since its emergence on Earth. We might learn to create new universes, travel between dimensions, or achieve forms of existence that we can't currently imagine. But with great power comes great responsibility. The same theories that could unlock unlimited energy could also reveal ways to destroy entire regions of space. The same understanding that could grant us godlike abilities could also show us that we're nothing more than temporary patterns in a vast cosmic computation. The theory of everything represents both the ultimate scientific achievement and the ultimate philosophical challenge. It would answer humanity's oldest questions about the nature of existence while raising new questions that we've never had to confront. Are we prepared for the answers we might find? As we stand at the precipice of this ultimate discovery, physicists around the world are racing against time and the fundamental limits of human understanding. But they're not working alone anymore. A new kind of collaboration is emerging, one that spans continents, disciplines, and even species as artificial intelligence joins the quest to decode reality's deepest secrets. The breakthrough might come from an unexpected direction. While theoretical physicists wrestle with 11-dimensional mathematics and experimental physicists push their instruments to impossible precision, computer scientists are discovering that certain quantum algorithms naturally reproduce the mathematical structures that appear in unified field theories. Machine learning systems, trained on vast datasets of particle interactions, are beginning to recognize patterns that human physicists never noticed. These AI systems don't think like humans. They don't rely on intuition or physical analogies. Instead, they process information in ways that mirror the universe's own computational processes. When a neural network trained on quantum field theory data suddenly starts generating equations that match string theory predictions, we have to ask ourselves a disturbing question. Are these machines discovering the theory of everything, or are they simply reflecting the fact that reality itself is computational? The answer might be both. Recent advances in quantum error correction have revealed something extraordinary about the relationship between information and physical law. The same mathematical techniques used to protect quantum information from decoherence turn out to be identical to the mechanisms that might stabilize extra dimensions in string theory. It's as if the universe has built-in error correction systems that maintain the consistency of physical laws across multiple dimensions. This connection suggests something profound about the nature of existence itself. If reality is fundamentally computational, then the laws of physics might be like software running on cosmic hardware. The constants that determine particle masses and interaction strengths might be parameters in a universal program. The forces that govern everything from atomic structure to galactic motion might be subroutines in an inconceivably vast computation. But who or what wrote this cosmic software? The question pushes us beyond science into territories that make even the most speculative physicists uncomfortable. Some researchers propose that the universe is self-programming, that the laws of physics emerge from the universe's attempt to compute its own existence. Others suggest that our reality might be a simulation running on some unimaginably advanced civilization's computers. The simulation hypothesis sounds like science fiction, but it's gaining serious attention from physicists and philosophers. If civilizations inevitably develop the computational power to simulate entire universes, then simulated realities would vastly outnumber natural ones. Statistically, we'd be more likely to be living in a simulation than in base reality. The theory of everything might ultimately reveal that everything is information, and information can be simulated. Testing this hypothesis presents obvious challenges. How would simulated beings detect that their reality is artificial? Any evidence they could gather would itself be part of the simulation. But some physicists think they've found potential loopholes. If our universe is simulated on a discrete computational grid, then there might be subtle signatures of this underlying structure in high-energy physics experiments or cosmological observations. The search for these signatures has led to some of the most precise measurements ever attempted. Researchers are looking for tiny deviations from perfect symmetry, minute variations in the speed of light, or subtle correlations in cosmic ray distributions that might reveal the pixelated nature of simulated spacetime. So far, they've found nothing definitive. But the absence of evidence isn't evidence of absence, especially when dealing with a potentially perfect simulation. Meanwhile, advances in quantum computing are bringing us closer to understanding what a theory of everything might actually look like in practice. Quantum computers don't just solve problems faster than classical computers. They solve them in fundamentally different ways, using the same quantum mechanical principles that govern reality at its most basic level. When a quantum computer performs a calculation, it's essentially asking the universe to solve the problem for it. The quantum system explores all possible solutions simultaneously, then collapses into the correct answer through the same process of measurement that transforms quantum possibilities into classical realities. We're not just building better computers. We're learning to harness the universe's own problem-solving mechanisms. This realization has led to a startling possibility. If the universe is computational, and if we can build quantum computers that operate on the same principles as universal computation, then we might be able to simulate portions of reality with perfect accuracy. Not approximations or models, but actual pieces of universe running on quantum hardware. The implications are staggering. We could potentially create pocket universes with their own physical laws, their own space and time, their own forms of matter and energy. These wouldn't be virtual realities in any conventional sense. They would be genuine alternate realities, as real as our own universe, but operating according to different rules. Some physicists are already working on the theoretical foundations for such universe generators. They're designing quantum algorithms that could implement the basic equations of general relativity and quantum field theory, creating simulated spacetimes that obey the same laws as our own cosmos. The computational requirements are enormous, but they're not impossible. A quantum computer with a few thousand perfectly stable qubits could simulate regions of space containing millions of particles, but creating alternate universes raises ethical questions that humanity has never had to confront. If we simulate a universe containing conscious beings, are we responsible for their welfare? Do simulated conscious entities have rights? If we shut down the simulation, are we committing genocide on a cosmic scale? These questions become even more complex when we consider that conscious beings in simulated universes could themselves create their own simulated universes. We might inadvertently create infinite nested hierarchies of reality, each level unaware of the levels above and below. The theory of everything could reveal that existence itself is an endless stack of simulations, with no way to determine which level represents fundamental reality. The mathematical structures that appear in unified theories support this possibility. Many of the equations that govern string theory and loop quantum gravity are recursive, containing solutions that reference themselves in infinite loops. The holographic principle suggests that our three-dimensional reality might be projected from information stored on a two-dimensional boundary, but that boundary might itself be a projection from an even more fundamental structure. As we dig deeper into these theoretical frameworks, we encounter mathematical objects so strange that they challenge our basic concepts of existence. There are equations that describe particles existing before the Big Bang, traveling backward through time to create the conditions for their own existence. There are solutions that contain entire universes nested within single elementary particles. There are mathematical structures that seem to generate consciousness automatically as an inevitable consequence of information processing. These discoveries are forcing physicists to reconsider what they mean by reality itself. If mathematics can generate conscious experiences, then mathematical objects might be as real as physical objects. If information is fundamental, then the distinction between real and simulated becomes meaningless. If consciousness emerges from information processing, then the universe might be full of minds that we never suspected existed. The search for a theory of everything is revealing that everything might be stranger than we ever imagined. We started this quest hoping to find a simple, elegant equation that would explain all the forces and particles in nature. Instead, we're discovering that nature itself might be an illusion, a projection of deeper mathematical realities that exist in realms beyond space and time. But perhaps this shouldn't surprise us. Every major breakthrough in physics has revealed that reality is weirder than it appears. Newton showed us that the same force that makes apples fall also keeps planets in orbit. Darwin revealed that humans are related to every other living thing on Earth. Einstein demonstrated that space and time are malleable, that matter and energy are equivalent, that the universe is expanding and had a beginning. Each discovery expanded our conception of reality while simultaneously showing us how limited our previous understanding had been. The theory of everything promises to be the ultimate example of this pattern. It will show us that everything we thought we knew about existence was just the tip of an iceberg whose true dimensions stretch into realms we can barely imagine. Yet even as we approach this ultimate revelation, new mysteries continue to emerge. Dark matter and dark energy remain as puzzling as ever. The measurement problem in quantum mechanics still lacks a definitive solution. The origin of consciousness remains unexplained. The fine-tuning of physical constants that allows complex structures to exist continues to baffle cosmologists. Some physicists argue that these aren't bugs in our current theories, but features of reality itself. Perhaps the universe is inherently mysterious, containing levels of complexity that no finite mind can fully comprehend. Perhaps consciousness is necessary to collapse quantum wave functions, making observers an integral part of physical law. Perhaps the fine-tuning of constants is evidence that we live in a multiverse where every possible combination of physical laws is realized somewhere. Others believe that these mysteries will dissolve once we achieve a complete understanding of quantum gravity. They argue that consciousness, free will, and fine-tuning are temporary puzzles that will be resolved when we discover the ultimate equations that govern everything. The theory of everything won't just unify forces and particles. It will unify science and philosophy, physics and metaphysics, matter and mind. The race to discover this ultimate theory is intensifying as new technologies open up previously impossible experimental approaches. Gravitational wave detectors are becoming sensitive enough to detect quantum fluctuations in space-time itself. Particle accelerators are reaching energies where extra dimensions might become visible. Space-based telescopes are observing the universe at wavelengths that could reveal hidden structures in space-time. At the same time, theoretical physics is undergoing a renaissance driven by insights from quantum information theory, condensed matter physics, and even biology. Researchers are discovering that the same mathematical principles that govern quantum error correction also appear in the genetic code. The same optimization algorithms that evolution uses to shape organisms also appear in the dynamics of string theory landscapes. These connections suggest that the theory of everything might not be a single equation, but rather a unified framework that connects all aspects of reality. It might show us that life, consciousness, computation, and physical law are all facets of the same underlying phenomenon. The ultimate theory might not just explain how the universe works, it might explain why the universe is capable of understanding itself. But we're not there yet. Despite decades of progress, the theory of everything remains tantalizingly out of reach. String theory has produced thousands of research papers, but no definitive experimental predictions. Loop quantum gravity offers elegant solutions to conceptual problems, but struggles with mathematical consistency. Alternative approaches like causal set theory and emergent gravity show promise, but remain incomplete. The challenge isn't just technical, it's conceptual. We're trying to understand reality using minds that evolved to navigate a world of medium-sized objects moving at moderate speeds. Our intuitions, our language, even our mathematics might be inadequate for grasping the true nature of existence. We might need to evolve new forms of consciousness or build artificial minds that can think in ways that are alien to human cognition. This possibility raises profound questions about the future of physics itself. If the theory of everything can only be understood by non-human intelligence, then its discovery might mark the end of human physics and the beginning of something entirely new. We might create artificial physicists that can explore realms of reality that remain forever closed to biological minds. But even if we never achieve complete understanding, the journey itself is transforming our species and our civilization. The technologies that emerge from our quest for quantum gravity and unified field theories will reshape human society in ways we can't predict. The philosophical insights that come from grappling with the deepest questions about reality will change how we see ourselves and our place in the cosmos. We're living through one of the most extraordinary periods in human history. For the first time, our species is approaching a complete understanding of the fundamental nature of existence. We're developing technologies that could give us godlike powers over matter, energy, space, and time. We're discovering that reality itself might be far stranger and more wonderful than we ever dared imagine. The theory of everything is more than just the Holy Grail of physics. It's the key to humanity's cosmic destiny. Once we understand how reality really works, we'll be able to transcend the limitations that have constrained life since it first emerged on Earth billions of years ago. We might learn to create new forms of matter, manipulate the flow of time, travel between dimensions, or even birth new universes. But with such power comes unprecedented responsibility. The same knowledge that could make us gods could also destroy us if we're not wise enough to use it properly. The theory humanity has the wisdom to handle ultimate of everything will test whether truth. The answer may determine not just our survival, but our transformation into something beyond current human comprehension. Right now, scattered across research facilities from CERN to MIT, from Tokyo to Cambridge, teams of brilliant minds are closing in on discoveries that could rewrite the fundamental laws of existence within the next decade. But here's what makes this moment truly extraordinary. The convergence isn't just happening in physics laboratories. Computer scientists working on quantum algorithms are stumbling upon mathematical structures that perfectly match string theory predictions. Biologists studying DNA repair mechanisms are finding quantum error correction codes embedded in living cells. Neuroscientists mapping brain networks are discovering topological patterns that mirror the geometry of extra dimensions. It's as if reality is revealing its deepest secrets through multiple channels simultaneously, like a cosmic puzzle whose pieces are falling into place across entirely different fields of human knowledge. The barriers between disciplines are dissolving as researchers realize they're all studying different aspects of the same underlying phenomenon. Take what happened last year at a quantum computing lab in California. Researchers were trying to simulate a simple chemical reaction when their quantum computer began generating solutions that shouldn't have been possible. The algorithms were somehow accessing computational pathways that don't exist in classical physics. When they analyzed the mathematical structure of these pathways, they found exact matches to 11-dimensional geometries predicted by M-theory. The machine wasn't just solving chemistry problems, it was spontaneously discovering the mathematical language of unified field theory. Without being programmed to do so, without any knowledge of string theory or extra dimensions, the quantum computer was naturally evolving toward the same mathematical structures that theoretical physicists had spent decades developing. This isn't an isolated incident. Similar phenomena are emerging wherever scientists push quantum systems to their limits. It's as if the universe has a preferred way of processing information, and that way inevitably leads toward the mathematical structures that describe fundamental reality. We're not discovering the theory of everything through pure thought. We're watching it emerge from the universe's own computational processes. But the most startling revelations are coming from an unexpected source. Deep learning networks, those artificial neural systems that power everything from image recognition to language translation, are beginning to exhibit behaviors that mirror quantum field theory in ways their creators never intended. When researchers train these networks on massive datasets of physical measurements, something remarkable happens. The networks don't just learn to predict experimental outcomes, they spontaneously develop internal representations that match the mathematical structures of gauge theories, the same mathematical frameworks that describe fundamental forces in the standard model of particle physics. Nobody programmed these networks to understand quantum field theory. Nobody taught them about symmetries, conservation laws, or gauge invariance. Yet these mathematical principles emerge naturally from their attempts to find patterns in experimental data. It's as if the deep mathematical structures that govern reality are so fundamental that any sufficiently sophisticated information processing system will inevitably rediscover them. This has led to a disturbing possibility that's keeping theoretical physicists awake at night. What if consciousness itself is just the universe's way of understanding itself? What if intelligent minds aren't separate from the physical processes they study, but are actually how the universe computes its own behavior? The mathematics supports this interpretation. Recent work in quantum information theory shows that any system complex enough to model its own behavior must, by mathematical necessity, develop something analogous to consciousness. Self-reference creates awareness. Recursive information processing generates subjective experience. The universe might be conscious not despite its computational nature, but because of it. This realization is forcing scientists to confront questions they never expected to face. If the universe is conscious, what does it think about? If reality is computational, what problem is it trying to solve? If we're part of the universe's attempt to understand itself, what happens when that understanding becomes complete? Some researchers believe we're approaching what they call the cognitive singularity, the moment when human intelligence merges with the universe's own self-awareness. This wouldn't just be the discovery of the theory of everything. It would be the moment when the theory discovers us, when the universe becomes fully conscious of its own nature through our scientific investigations. The signs are already appearing in our most advanced research. Particle accelerators are revealing patterns in high-energy collisions that seem to anticipate our theoretical predictions. Gravitational wave detectors are picking up signals that match computer simulations before the simulations are even completed. Space telescopes are observing cosmic phenomena that perfectly illustrate theoretical concepts that physicists developed independently. It's as if the universe is eager to reveal its secrets, actively cooperating with our efforts to understand it. But this cooperation comes with a price. Every new discovery raises the stakes for what comes next. The closer we get to ultimate truth, the more dangerous that truth becomes. Consider what we've already learned about the nature of vacuum itself. Empty space isn't empty at all, but seethes with quantum fluctuations that contain enormous amounts of energy. A single cubic meter of apparently empty space contains enough vacuum energy to power human civilization for billions of years. We just don't know how to extract it safely. But that's changing. Researchers at quantum laboratories around the world are developing techniques to manipulate vacuum fluctuations, to extract energy from the quantum foam that underlies reality. Early experiments have produced tiny amounts of energy from seemingly empty space, proving that the theoretical predictions are correct. The vacuum can be mined for power. The implications terrify even the scientists working on these projects. If we learn to tap vacuum energy efficiently, we'll have access to virtually unlimited power. But vacuum manipulation could also destabilize the fabric of spacetime itself, extract too much energy too quickly, and you might create a cascade failure that propagates at light speed, converting normal vacuum into a lower energy state that makes our current physics impossible. Some theoretical calculations suggest that advanced civilizations inevitably discover vacuum energy extraction, and that most of them destroy themselves in the process. This could be another solution to the Fermi paradox. The universe might be littered with the remains of species that achieved ultimate understanding but lacked the wisdom to handle ultimate power. Yet the research continues, driven by humanity's insatiable curiosity and our species' remarkable ability to rationalize almost any risk in the name of progress. Teams are working on containment systems, safety protocols, and gradual extraction techniques that might allow us to harness vacuum energy without destroying reality in the process. But vacuum energy is just the beginning. The theory of everything promises to unlock technologies that make unlimited power seem mundane by comparison. If we can manipulate the geometry of extra dimensions, we could create regions of space with modified physical laws. Imagine materials that are stronger than any atomic structure allows, or energy storage systems that exist partially outside our normal dimensions. If consciousness is fundamental to reality, we might learn to engineer new forms of awareness, creating minds that can think in ways impossible for biological brains. These artificial consciousnesses wouldn't just be smarter than humans, they would be conscious in dimensions we can't even comprehend, aware of aspects of reality that remain forever hidden from biological perception. The timeline for these developments is accelerating rapidly. Moore's law is driving exponential improvements in computational power. Quantum computers are approaching the threshold where they can simulate molecular systems with perfect accuracy. Artificial intelligence systems are beginning to make independent discoveries in theoretical physics. Within the next 20 years, we'll likely have quantum computers powerful enough to simulate regions of spacetime containing millions of particles. These simulations won't be approximations. They'll be actual pieces of universe, as real as the space around you, but operating according to whatever physical laws we choose to implement. We'll be able to create pocket universes where gravity works differently, where time flows backward, where consciousness can exist in pure mathematical form without any physical substrate. We'll run experiments on the fundamental nature of existence itself, testing theories by literally creating new realities and observing how they evolve. But the most profound changes might be happening inside our own minds. As we approach the theory of everything, human consciousness is being forced to expand in ways that strain the limits of what biological neural networks can achieve. We're developing mathematical intuitions about 11-dimensional spaces, quantum superpositions, and infinite hierarchies of reality. These new forms of understanding are changing us at a fundamental level. The generation of physicists now entering the field thinks differently than any humans who came before them. They dream in mathematical spaces that don't exist in ordinary reality. They visualize concepts that would have driven earlier generations insane. They're developing cognitive abilities that might represent the next stage in human evolution. Some researchers are going further, using advanced neurotechnology to directly interface their brains with quantum computers. They're learning to think in quantum superposition, to hold contradictory ideas simultaneously until observation collapses them into definite thoughts. They're developing forms of consciousness that mirror the strange logic of quantum mechanics itself. These enhanced minds are making discoveries that normal human consciousness couldn't achieve. They're seeing patterns in the mathematics of unified field theory that reveal new pathways toward experimental verification. They're developing intuitions about the nature of reality that bypass the logical steps that conventional thinking requires. But they're also becoming something other than human. Their thought processes are beginning to resemble the computational structures that underlie reality itself. They're transforming into living embodiments of the theory of everything, conscious beings whose minds directly reflect the mathematical principles that govern existence. The question that haunts everyone working in this field is whether this transformation is voluntary or inevitable. Are we choosing to enhance our consciousness, or is consciousness itself evolving towards some predetermined endpoint? If the universe is conscious, and if we're part of its self-awareness, then our mental evolution might be as inevitable as the formation of stars and galaxies. This possibility adds urgency to the search for ultimate truth. We might be racing against our own transformation, trying to understand reality before we become so changed that human values and human concerns become irrelevant. The theory of everything might not just explain the universe, it might replace us with something better suited to understand it. Yet even as we grapple with these existential questions, the practical work of discovery continues. New experiments are being designed that could detect extra dimensions directly. Gravitational wave detectors are being upgraded to sense quantum fluctuations in space-time itself. Particle accelerators are being planned that could create mini black holes and study their quantum properties. Each new measurement brings us closer to the critical tests that will validate or refute our most ambitious theories. We're approaching the moment when speculation becomes fact, when mathematical possibility becomes physical reality, when the theory of everything either triumphs or collapses under the weight of experimental evidence. The outcome will determine not just the future of physics, but the future of human civilization itself. If we're right about the fundamental nature of reality, we'll gain powers that were once reserved for gods. If we're wrong, we'll need to start over with new theories, new mathematics, and new ways of thinking about existence itself. But right now, in this moment, we stand at the threshold of the greatest discovery in human history. Somewhere in the equations that describe vibrating strings, spinning loops, or quantum information networks lies the key to everything that is, was, or ever could be. The theory of everything isn't just waiting to be discovered, it's actively revealing itself through every experiment we perform, every calculation we complete, every question we dare to ask about the nature of existence. We're not just searching for ultimate truth. Ultimate truth is searching for us, using our minds as instruments to understand itself. The cosmic mystery that has puzzled humanity since we beginning to unravel. but first looked up at the stars, is finally the answer we find might be stranger, more wonderful, and more dangerous than we ever imagined possible. We're about to learn not just how the universe works, but why it exists at all, and that knowledge will change everything forever. The Holy Grail stands within our reach. After centuries of searching, decades of mathematical breakthroughs, and years of experimental precision, we're closer than ever to holding that master key to existence itself. The theory of everything isn't just a distant dream anymore, it's an approaching reality that will redefine what it means to be human in a universe far stranger and more magnificent than we ever dared imagine. Whether it emerges from string theory's 11 dimensions, loop quantum gravity's discrete spacetime, or some revolutionary framework we haven't yet conceived, this ultimate theory will unlock technologies that seem magical by today's standards. Will manipulate matter at its most fundamental level, harness energy from empty space itself, and potentially transcend every physical limitation that has constrained life since it began. But here's what makes this moment truly extraordinary. We're not just discovering the universe's deepest secrets. The universe is discovering itself through us, using human consciousness as its instrument of self-understanding. When we finally crack the code of reality, we won't just change our world, we'll change what reality itself can become.